If I want to build the regression equation for our linear model, the actual method for computing these ideas involves us looking at our scatter plot and measuring a bunch of distances. Those distances are the distances from my prediction line to the data points themselves. So I would have some scatter plot looking like this. And I notice that each point has some distance above or below this predicted line. Now, it turns out that the method by which I find the equation of this line is to do enough calculus to find the smallest possible distances here. That means I need to measure the distance from top to bottom there for all of these dots against that line. Measuring distance is hard because it involves taking the square root. And some of those are positive and some of those are negative, and that's kind of ugly. So to get rid of the negatives, we square everything. And the formulas that can be produced from this method are disgusting. I'm going to tell you right now. I cheated. This is the calculus book, not even our stats book. I never want to do this by hand, ever. But the method we are doing is called the method of least squares regression. Sometimes it's referred to as ordinary least squares, so you'll often see it abbreviated OLS. This ordinary least squares regression is designed to find the y-intercept and the x-intercept of this line. Sorry, the y-intercept of the slope. But if I don't want to do this by hand, how the hell am I going to come up with this? I need a sample scatter plot. Here, problem 13 from our text compares home prices with median income in that area. Everything in here is in thousands of dollars. So let's make a scatter plot of this. Here is our scatter plot showing what kind of a relationship? Looks like a positive one to me. As median income increases, home prices appear to increase. But this isn't a very narrow band of dots. This is kind of spread out. So I would expect my correlation to be positive, but not really all that close to 1. If I already have the scatter plot, I can simply create the exact equation I want in Excel. Right-click on one of the data values within our chart, and I get a bunch of options. Down there, it says add trend line. The trend line is exactly the option I want to create the line that fits these the best. Add trend line. Boop. And when it adds the trend line, it gives me a whole bunch of options for my trend line over here on the right. Now, this is where I say that I'm just looking at linear fit, right? I'm looking at a line. But notice there's a whole bunch of other models over there on the right. There's an exponential model, a logarithmic model, a polynomial model, a power model, a moving average model. All of these are variations on the same theme. I'm really only concerned about straight line behavior right now. But as we said earlier, we had data on Monday that looked like it was in the shape of a parabola. I could do a polynomial fit and try and make a parabola that fit that data. There are transformations that turn all of these data into linear behavior. So if I know how to do the line, do the rest. Trend line name, I didn't name it. It made it automatic. I've got a forecast option. When I have lots of data, I could predict by extending this line to the right or to the left, forward or backward forecasting. That gives me a number of periods. In this case, the dollar. But underneath that, it's got 3 options. There are cases where we want the intercept to not matter. Remember what we talked about at the end of Monday? Does the intercept have meaning in this setting? We had one where we were talking about home prices based on square footage. And when the intercept was 0, that was the price of a house with no square feet. In other words, the price of the land. And then we had one where car thefts in terms of age, but I don't know how to have an age of 0 for a neighborhood. I can set the intercept if I want to make the intercept not an important part of the way this data works. But underneath those, the bottom 2, one says display equation on chart. That's the one I need. If I check display equation on chart, boop, there's my equation. I can't really read it, so I'm going to change the text size. Where's my font option? Oh, maybe if I just drag this box and make it bigger, that'll help. Nope. I have to actually drag the box. There's my font size. Now I can read it. Yes, sir.
Can I get to this sidebar again?
When you go to right-click on the data values themselves, on one of the actual dots, right-click on it, and then it should say add trend line.
Yeah.
All right. I have the equation sitting here. So now I get to ask some questions about what does this mean? First question, what's the slope mean here?
How much positive is the correlation?
Unfortunately, no. The slope simply tells me that the being positive, that there is a positive correlation. How good the positive correlation is isn't actually up here at all yet. I have not put forth the correlation coefficient. That's not on here yet. I'll get it, but it's not there at the moment. What does that 2.6 mean? Yep.
I mean, like the y-intercept was 51.2 and the slope is like positive 2.6.
Right, the slope is positive 2.6, the intercept is 51.2, that's the algebraic expression. In terms of this setting, what does that 2.6 represent?
Just remember that y is strongly affected by x.
That is only measured in our correlation coefficient. Correlation isn't up here. It tells me how much y is affected by x, right? That's what the slope of a line does. It tells me how much we're increasing or decreasing. In this setting, rise over run is the slope. What are the units for rise?
Would be income
And income is measured in
dollars.
this case, thousands of dollars, right? And the run units, that information is right up there in that blue box. The run units are income. That's also measured in thousands of dollars. So what does this mean? It means for every additional $1,000 of median income, home prices do what?
There's
By
2.6.
2.6 thousands of dollars. I knew from my ANOVA that I could just say, hey, things are going up. But now I can tell you exactly how much. For every $1,000 increase in median income, there should be a corresponding $2,600 rise in home prices. Having the equation doesn't just tell me that they are affected. It doesn't tell me how well this regression fits, but it tells me that relationship between the affected relation variables. What's the 5126 mean? 51.246.
Y-intercept.
Geometrically, yes, it's our y-intercept. What would it represent in this scenario?
Doesn't it represent like the lowest, would it be income? Or like,
You said it was a y-intercept, so it should be somewhere on here, right?
yeah,
Y represents income or home prices.
home prices,
So that's a home price.
yeah.
It's a home price when what income happens?
You know,
Does that make any sense at all? If a neighborhood has a net median income of 0, that neighborhood is in deep shit. So while that is the correct interpretation, it isn't a useful number for me to say if everybody in this neighborhood was broke, a house would sell for $50,000. Nobody's buying that house. So while that is the correct interpretation, it isn't meaningful in this setting. But now I could predict if the median income was $40,000, that's not a number that's any of my data in here, is it? But I could take that equation and plug in 40, and you could tell me how much a house would go if the average income in that neighborhood is $40,000. sorry, median income, right? Median family income. What's the price of a house if the neighborhood income is $40,000? Humble. Okay, what you got?
I got 104,443 and 25 cents. Right, wrong.
Did I enter it wrong?
Wait,
$40,000 times my slope,
why do you only put 40?
because back here,
You said that it was like in the thousands, but. Instead of, but.
since they're both in thousands,
Mhm.
if I put in the number as 40 rather than 40,000,
Yeah,
then I have 40,000 times 2.6 plus 51 is already in thousands. Both sets of numbers are in thousands. So if the median income is in 40,000, I'm only gonna enter 40. I have to make the units match. And that's this sentence right up here, that everything is in thousands of dollars already.
so. So that,
I've got to make sure both. The 51 is already in thousands of dollars, right? So that's why this is $155,000 home price. I'm not sure this is a reasonable model. I don't know where they're buying these houses. But I don't know if you can pay for a $155,000 house on a $40,000 income. It used to be true. I'm just not sure it is today. Questions? If I knew the neighborhood was $100,000 a year, I could put in 100 instead of 40. If I knew the neighborhood was 20,000 a year. Now I may not be able to go generalize this data because this data may be too limited. I only have 34 cities. They're all eastern cities. Virginia, New Jersey, Tennessee, North Carolina, Florida, Georgia, Lower Mayfield Township, Pennsylvania. I don't know where these places are. So this might not generalize because we're further west. It might not generalize at all if you go out way further west. I'm not going to apply this to California house prices. Wouldn't be an appropriate list. My data is limited unless its application is limited. I still, though, have not figured out how good a fit this is. Now, I could find the correlation coefficient. We had a command for that. What was the command for our correlation coefficient? Keep it on Monday.
it's Corel.
The start of the word correlation. So if I type up here in one of these boxes equals CORREL parentheses, highlight the income list, comma, highlight the home price list, I get a correlation of 0.5829 according to that list of decimals. What does that number tell me?
How close all the dots are to the line, so it's like closer to 1 or 0, so it's if there's a correlation.
The closer we are to 1, the more straight line this data is. The further we are from 1, the closer we are to 0, the more scattered and random this data is. Alessandro, this is what tells me how strong the relationship is. But there's actually another way to think about this. Let me go back to our trend line. And here are all of those options for the trend line. If I just click on the trend line now, I'll pull back up the trend line option. The last checkbox on the right says display R squared. Take that number 0.582994 and square it. What do you get? There are a bunch of you sitting with computers open in front of you, not doing calculations. Go into Excel, type equals that number squared.
0.53988.
I don't know why my box is not showing this. Let's go back to the trend line. Uncheck, uncheck. There's my R squared value. 0.3399. Okay, let's call it 34. 0.34. What does this mean? The square of our correlation coefficient is called the coefficient of determination. This is always between 0 and 1 because it's a square, right? It's always going to be positive or 0. This is often thought of as how much of the variation is explained, is determined by our variation in X. This tells me that 34% of the variability in home prices is due to variability in income. If this was a perfect straight line, this number would be 1. 100% of the home price changes would be due to change in income. But this says only 34% of the change in the price of a house is due to the change in the income. And that means that 66% is due to other stuff. There's other determining factors other than the X values we picked, the income. This is why this is called simple regression. It's only attempting to take one factor into account, like our ANOVA. It is always the case that the coefficient of determination is the square of our correlation. Questions? Here, portfolio returns last year versus we saw this one before, right? We did this last time. I can ask about a confidence interval. How sure am I of this equation? How confident am I that this is the right equation? But in order to do a confidence interval, I need a standard error. That was what we did to find the z and all that stuff for confidence interval. I do not want to do this by hand, ever. The formulas for confidence interval will require me to do standard error. Suck. This is the standard error for my slope. This is the standard error for my intercept. I don't want to do this. Fortunately for me, I don't have to. Rather than build the scatter plot first, I'm going to ask Excel to do all of the regression and all of the error calculations and all of this in one fell swoop. Just like I did with the ANOVAs, just like I did with the histograms. I'm going to go to my data analysis toolpack. Under data analysis. There it is. Regression. If I click on that, it'll say, all right, where are your Y values? It starts Y first. Now it actually labels this year as Y in our data, so I'm going to use that. Notice I am highlighting the name itself. Means I got to check the labels box. Where are the input X ranges? Again, I have to click the labels box because I've included the label. So click labels box. And down here, it gives me all these options again. I'm going to have it put all of this in a new page, new workbook apply. But I want it to give me a bunch of stuff. There are lots of things there. We'll get back to that. Not going to have it do any of that right now. This is what it spits out at me. What the? What is this? That's a lot of a mess, isn't it? Correlation information is in the last rows. Let's go down here. Those last two rows are labeled intercept and X. Those are my numbers, M and B. Coefficients, right here. Those two numbers give me my linear equation. Well, now I know the equation I want. Y equals mx plus b. There's my slope. There's my intercept. 0.04579, however many decimal places you want, x plus 11.15. There's my equation. Next to those are the standard errors. And lo and behold, at the end here, on the right, is a confidence interval for each of those numbers. Now, it actually shows up here twice. By default, it gives me a confidence interval of 95% in these first two boxes. And then these last two boxes, it gives me a confidence interval at whatever other confidence I told it to use. I didn't tell it another confidence. So it assumed I wanted 95% again. I don't know why it gives it to me twice. I think that's dumb, but I didn't write it so. Okay, hang on a second. My 95% confidence interval for the slope for X tells me that confidence interval goes from 0.056 to 0.8598. Think about a t-test versus a confidence interval. or a z-test versus confidence interval. Our null hypothesis from Monday, when we thought about are these things related, we were able to say, hey, if there's a t calculated, we can do, right? Gave you formulas for that crap. Is this related? Our null hypothesis was that there was no relationship. Our alternate hypothesis was that there was. My confidence interval goes from 0.06 to 0.86. What's not in that confidence interval that would be important in terms of those hypotheses? Hypothesis test and a confidence interval are related to each other.
I've used that game to see if the slope is ever 0 or not.
My null hypothesis was that my slope would be 0. Correlation would be 0. This confidence interval doesn't contain 0.
Therefore, we reject it.
And that means my alternate hypothesis is true. There is a correlation here. I can even check the p-values that are right here. And that p-value is 0.03, which is smaller than 5%. There is a correlation. And it's strong enough for me to say this is a good predictor that last year's rate of return does affect this year's rate of return. As a matter of fact, I know the same thing up here. Here's the p-value for our f-test. The f-test, they did an analysis of variance. There's an ANOVA in the middle of my regression. You got your ANOVA in my regression because it's in there. That's what our correlation of our coefficient of determination is telling us how much of the variation is responsible in each direction. And that is also less than 0.05. As a matter of fact, it's the same number here. That is not a coincidence. So I know not only that there is a relationship, I know that my intercept and slope are accurate enough for there to be a cause here. And I can tell you how much it is. Now, you'll notice I didn't generate the scatter plot. But what do you see at the top of this as I work my way up? We went from the regression itself, which is at the bottom, to the ANOVA, which is right above that. What's above that? Those two numbers. Take the first one and square it. What do you get? The second one. That means that first number is our correlation coefficient. And that second number is our correlation of coefficient of determination. So according to this, 28% of the variation in this year's returns for these mutual funds is related to the variation in last year's earnings. But this is a stronger relationship. 0.53 and R bigger than a half, we're closer to 1 than 0. Please notice what they didn't give me in the ANOVA is an F crit, but they gave me the p-value under that significance F, so that's good enough for me to be able to test whether or not this variance is unusual. Questions? I didn't draw a squat, but we could go back and draw the scatter plot, right? I know how to do that already. But I just said, I think there's a relationship here. And all the numbers I needed to say, yes, there is a relationship here, are here in front of me. And I can tell you it's a positive relationship. Why? I don't have a picture. How do I know it's a positive relationship?
Because of R.
R just tells me how strong the relationship is. But R is positive. But even more than that, so is my slope, right? My slope is a positive number. 0.45, 7, whatever the rest of that is, right? We're going up. Positive R, positive slope, we're going up. Perfect. Question everybody asks me with finals coming up. Does studying more help? 10 students were surveyed. How much time did you spend studying? And then I looked at their exam scores. Is there a relationship between how long a student studies and their exam score? Maybe. Let's find out. At least in this group, let's find out. Do you think so? There's my scatter plot.
What's the name of this?
This is chapter 12, section 4, example, exam scores.
We can look at the trend line.
I can look at the trend line, so let's add it on here. I right click on one of these data points and I click add trend line. Yep, it's going up. If I ask it for the equation and the R value, I see a positive slope, 0.196x plus 49.47. We're going up. More studying, higher score. R squared is 0.394. What does that mean? What do we call that number? Speaking English, right? Esperas. Tenemos que hablar en español. Come on, talk to me. What did we call that R squared thing? We gave it a name. Coefficient of determination. Determination. So that tells me 39% of the variability in exam score is due to variation in studying time. That means that there's another 60+% of reasons people got different scores that has nothing to do with how long they studied. So while studying helped, and I can tell you how much it helped, there are other factors involved outside of how long I study. But yes, studying does help. If I do the full ANOVA calculation with all of the bits and bobs from data here, data analysis, regression, study hours goes from here to, oh, no, Y first. Exam scores goes from here to here. X second. Study hours goes from here to here. Labels, I included the labels. .964 is the slope. 49.477, that's my intercept. They're the same numbers we saw in the scatter plot. Correlation, R squared, coefficient of determination. They're both up there. 0.6277, that means it's closer to 1 than 0. There is a relationship. But is it significant? Look at your X value, study hours. Look at your confidence interval there.
Would it be bigger than alpha?
The p-value is bigger than alpha. The confidence interval includes 0. Can I reject my null hypothesis? No. It is quite possible from this set of data for me to say how long you study does not have any effect on your exam score. In spite of the fact that I saw what looked like a correlation, the R value tells me it's strong. It's not strong enough. This data doesn't support the idea that studying more guarantees you a better grade. Now, I'm pretty sure I can blame this on one person. Because if I go back and look at this data, I don't know what Noot was doing, but he studied for 15 hours and earned a 69 on the exam. Ow. That probably threw my data off a little, wouldn't you say? But down there at 1 hour, a 53 meant that that end came up. So there's something to be said for the way the scatter plot looks. But there's something else going on here. And I don't know what it is. But this isn't the sole explanatory variable. I would like to be able to look at how far off those data points are from my line and do some analysis on that idea. I'd like to understand if any of these are particularly important XY points, or if any of them particularly affected what I think is going on. As I just said, this one on this end and this one low on this right end, they probably have something to do with it. How can we be sure about that? That is what we will discuss Friday. See you all then. Have a wonderful rest of your day.